is Mike Resso. I'm a signal integrity applications scientist from Keysight Technologies. I've been working in the test and measurement field for a few years, looking at frequency and time domain analysis of high-speed digital interconnect. And today what we're going to do is show you a very simple way of removing fixtures and or probes from your PCB trace measurements. And of course, any linear passive device under test will work just as well. Backplanes, connectors, cables. Today we happen to have a nice test vehicle from Brian Shoemaker from GigaProbes. So let me introduce the equipment that we're going to be using for this experiment. Right now we're using an Agilent PNA. It's a N5245A Vector Network Analyzer up to 50 gigahertz. We're running N5245A physical layer test system software, PLTS, on a laptop, and we're connected from the laptop to the Vector Network Analyzer with a USB to GPIB interface. Very easy connection for communications. We can control the calibration and the measurements of the VNA, and then afterwards do post-measurement analysis on the PLTS software. On the probe setup, we have a very nice, easy to set up system from GigaProbes. We have 2 differential probes working up to 40 gigahertz with a small camera system and magnetic bases, and you can see how we get coplanar probe placement on a differential PCB trace with our system here. And so what I'd like to do is briefly talk about error correction because calibration, de-embedding, all of these terms are a bit confusing. And to set a perspective, we can look at various error correction techniques, and we can somewhat plot accuracy versus simplicity. And here you can see there's pre-measurement error correction, like reference plane calibration, normalization, short open load through, LRM, TRL. This is all what we call calibration or pre-measurement error correction. And then with the red triangles, we have what's called post-measurement error correction. De-embedding, once you have the S-parameters of the structure you want to remove, you can do de-embedding. Port extension, time domain gating, and then the new game in town is called automatic fixture removal, or AFR, and that's what we're going to show today. And so there are many different ways to skin a cat. The way that we're going to do it today with AFR is going to probably save on the order of 30 times the amount of time spent. A TRL calibration kit, once you design it, fabricate it, use it, it's going to cost, who knows, $5,000 to $10,000, and the measurement will take maybe a couple hours. With AFR, you don't need to build any special cal kit. All you need is to put an open or a short at the reference plane that you want. So for example, in our system here, we've got probes. We want the reference plane to be at the probe tip. So all we have to do is put a short or an open at the probe tip, and that's the calibration. So to be more specific, what we've done here with this system, we've done first an SOLT with an ecal. So we've done a short open load through to the end of the test cables. So we've got a coaxial environment with SOLT. But what we really want is the reference plane down here at the end of the probe tip. And so here, we're going to actually use AFR. We're going to derive the S-parameter model of the probe by using an AFR SDD11 measurement. And with that one reflect measurement, we're able to get the complete model of this probe and then de-embed that inside AFR and get just the measurement of the trace. So let's show how that happens. we've made a measurement in PLTS, and of course we could look at frequency domain parameters, or we can look at time domain parameters. It's just an FFT or IFFT. I like to look at TDR impedance profile, and so here you can see what we're after is these structures right here. We want to end up with just these two large inductive spikes plus the PCB transmission line. We want to get rid of everything else, which is the probe and the associated adapters with the probes. And so the way we want to do that with automatic fixture removal is first we make the complete measurement after an SOLT at the end of the test cables, which is what we're showing here. And then we simply go into automatic fixture removal in PLTS, and you choose the wizard. And here we have an intuitive interface with a graphic that will change topology based on whatever application you have. And so you can look at the graphic to make sure that you've got the right exact topology. And so what we're doing now is we've got differential measurements with a 4-port system, and step 2 is we specify the standards. Now, as I mentioned, all we're going to do is use a short at the end of the probe tip as our only calibration standard. We could use an open, or we could do both if we wanted to, but it's not necessary, open or short. So we're going to use a short, and so we can either measure the short or we can load them. So to save time, we've actually used a shorting block, and we landed the probes onto a shorting block and got an S2P file, which is basically the differential reflect. And that's all we need to get the whole S-parameter model of the probe. And so all I need to do now is to load that data, and you can see here I've got that. It's an S2P file. It's about 400 kilobytes in size. That's 20 gigahertz data, and I'm just going to load that into the AFR wizard. And I've got to do that for both probes. And in our case, both probes are identical, so we can load the same file. And here we've got some calculated probe characteristics, which it's very close to 50 ohms, which I would consider typical. And now we go to removing the fixture. And in this case, fixture A is really probe A, and fixture B is really probe B. And so what I want to do is I want to actually semi-collapse this dialog box, show the impedance profile of the complete channel before I implement AFR, before I remove the probes. Now, if I hit this button that says apply correction, then what I'm going to do is I'm going to remove all this other extraneous material, and I'm just going to view this transmission line and the two inductive launches at the probe site. So here I apply correction, and I'm going to do a nice auto scale for you, and now you can see that we've removed all of that extraneous data that was really not correct, because the loss and reflections from the probing system was interfering with the real data. So the true impedance of that trace we can measure by inserting a marker in the middle, and we've got a value of 103 ohms. If I go back and undo AFR and remeasure that, we can see what the improvement in accuracy is of that impedance. So let's do that. We'll undo the correction. We're going to auto scale. We're going to place the marker 98.5 ohms. So we went from roughly 99 ohms to 103. That's 4 ohms difference. Well, that doesn't sound like a lot, 4% out of a 100 ohm environment, but that's 4% of margin that you're giving away that you don't need to. And so, very similar to the way that we apply and remove the correction in the time domain, you kind of get a nice feeling for what is being affected by the probes. We can do the same undo and apply in different domains. So just like we applied automatic fixture removal in the time domain, and we analyzed the impedance profile before and after removing the probes, we can do that same exact thing in the frequency domain, although it may not be as pronounced as of a difference. So if we look at the SDD21 of the complete channel, including the probes, this differential insertion loss has this type of slope to it. And you want to just look at the top envelope of this differential insertion loss curve. Now if I go and apply the AFR correction, you'll notice that it will bump up slightly, but not a lot. And what that means is that there it is, the quality of the probes, the bandwidth of the probes is quite high. So it's good to use the best quality probes you can. You don't want to make the mistake of, well, I'm going to de-embed the probes anyway, so it really doesn't matter how good the probes are. That doesn't really hold at all. You want to get the best PCB material, you want to get the best probes, you want to be able to really get the best quality of signal integrity measurement before any of this error correction happens. And so, in conclusion, what we've shown is probing with a VNA and driving the automatic fixture removal technique with physical layer test system software, we're able to first do a coaxial calibration to the end of the test cables, and then we're able to, by just simply looking at a reflect of the probe, we're able to remove all of the probe effect, which is just as accurate as a de-embedding, because AFR allows us to extract the S4P information of the probe, which is the model. And so this is a very accurate methodology. It's becoming a standard in many of the high-speed digital interface committees. And so rather than struggling with through reflect line calibration kits, which require a lot of time and money, you can actually save a lot of time, a lot of money, and use this newer automatic fixture removal technique. And the probing system for this does not have to be extravagant or sensitive or fragile. You can have very robust probing system that allows you to make a wide variety of measurements in high-speed digital applications. Thank you for your time.